Hmm?
By the way, for the exception.
Oh, of course. Yeah, of course.
Just when I thought one medical thing was done, then I got a second one this big, and I'm like, this is back when you get older.
Oh man, yeah. It's everything always happens at once.
Yeah. It's already hit 28. I'm like, my coworkers are all like 30.
Yeah.
They're like, oh, wait till you get 30. That's a good number when you're gonna start feeling everything. Because I told my ACL, right?
Uh-huh.
They're like, just wait. And so then now I'm 28. They're like, you're falling apart faster than us.
I know, I'm 32 and I feel what everybody do. It's like, oh my God. Back, everything.
I know.
This thing that I hurt like 3 months ago, it's not healed yet. Come on, body.
Yeah.
You're better than this.
Like this recently I got a CT scan, right?
Mm-hmm.
And so right when I get home and I get my backpack and look through a one hand like I always do.
Yeah.
And like my bicycle strains. I'm like,
oh,
you can't do anything right now.
Dude, I mean, we're all, yeah, it's that age.
Yeah.
It always feels like it happens so fast too, even though it's like kind of a slower breakdown, but like you don't feel it until a certain point, and then it feels like oh my God.
Yeah. It's long recovery. More excuse for me to go on travel.
That's true. It's fair. It's fair.
How's your fantasy team coming along?
I'm not playing this year.
Oh, you're not playing this year? Oh, I thought you were.
I stopped a while ago. It's I feel like I enjoy football more than I'm playing fantasy. It's like too much. It's like too much to keep track of it and manage.
Yeah.
Hey, Professor,
Mhm.
I have a question.
Sure.
So I'm taking the cardiovascular class next.
Yeah. Uh-huh.
Which one do you think is like more like challenging between this one and cardiovascular?
This class is a little bit more traditional, I would say, and so this is kind of a more traditional biomechanics course. The cardiovascular course is more unique, and so I think it's there's not as many resources out there. I would say we're going to be using a research software too for cardiovascular. So I guess it depends how you feel in terms of statics and dynamics versus fluid mechanics. Because cardiovascular is much more fluid mechanics. And so if you think fluids was harder than kind of dynamics and solids, then you'll probably find the cardiovascular more difficult.
You was the only class I like open night schedule, so it was okay.
Okay.
And it also seemed interesting to me.
Yeah. No, it'll be a fun class. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, doing good. All right, so today, I do have a couple announcements, but the plan for today is we're going to finish up our lecture notes on human motion kinematics, and then we're going to move on to dynamics. Okay. And so the dynamics portion, I think we'll probably start it today. We'll finish it up next Monday. I always forget what day it is. And then that'll be kind of the cutoff for the next midterm. Okay, so this next midterm, remember we're having it on the Wednesday before Thanksgiving, so that's Wednesday, November 15th. And so the cutoff is going to be for dynamics, right? And so with that in mind, I did post the next homework. And so I posted that just about an hour ago. And so that homework is about kind of this human motion kinematics and the dynamic stuff that we've been covering. Okay. So make sure you take a look at that. It's a little bit more, a little bit more calculation intensive than the previous homework. So definitely make sure you check it out and get started on that. Okay. Okay. Any questions before we get started for today? Okay. Okay. So before we start today, I did want to show you something. It has absolutely nothing to do with the class. It's just kind of funny. So recently I've been going through a lot of old photos just because I'm planning a wedding for the end of this semester, and so we're going to show a lot of like our old baby photos, childhood photos, things like that, as is usual. So I found this one picture, and so this kind of goes along the lines of like if you ever want to grow up and teach engineering at a college, you have to be a pretty big fucking nerd to do that. And so this is just to kind of show you that I've always been like this. It's not just a recent thing. So this is from 2011. So this is my sister's high school graduation. So like a really big achievement for my sister. And this is me. And if you look at this textbook here, some of you may recognize this. This is the freaking fluid mechanics textbook. And so if you guys are taking 333 right now, or if you've taken 333, that's the textbook that you guys are probably using. And this is me studying it at my sister's high school graduation in 2011. So I've always been like this. And so my mom sent me this picture and she's like, "What are you doing studying a textbook at your sister's graduation?" I'm like, "I don't know. I guess I was just born to do this." So anyway, I thought that was just kind of funny. Thought I'd share with you guys. Okay. All right, back to the actual class here. Okay, so let's get back to it. So we just have a little bit more to do in terms of human motion kinematics. And so what I want to do is I just want to cover this last section here, and then I want to cover the homework a little bit too, just because the homework problems regarding this section is a little bit different than what we've been going over in the class. So I want to make sure you guys are kind of know how to get started with those problems. Okay. Okay. So actually, let me kind of scroll up here a little bit and just kind of remind you kind of where we left off. Okay. And so last time in class, we talked a lot about this idea of using transformation matrices, right? And so ultimately, the goal in human motion kinematics is we want to be able to track the joint angles in a person's body as they go through motion. Okay. And mathematically, the way that we're going to do this is through these transformation matrices. Okay. And so in 3 dimensions, our transformation matrix looks like the following, right? Because for a general joint, and so, kind of regardless of if you have like a hinge joint or a ball and socket joint or whatever, when you're in 3 dimensions, you have, basically 3 angular degrees of freedom, right? And so we call those 3 angles theta, phi, and psi. Okay. Okay. So this is kind of what we were working with here. And so the idea is that if you can compute this, or I should better say, if you can track this, throughout a person's motion, you'll be able to, computationally compute, what the joint angles of that person is throughout time. Okay. Okay. And so basically the goal with any motion capture or any kind of setup that you're using for human motion kinematics is to obtain this matrix, right? So this matrix is kind of your holy grail for this. Okay. Okay. So let's talk a little bit about how we can obtain this, because we've kind of we've talked about kind of a lot of kind of ideas that are kind of a little bit kind of separate from each other. We've talked about, the motion capture trackers. We've talked about kind of the anatomical reference frame, the tracking reference frame. We've talked about transformation matrices. And so now is kind of the time to kind of put it all together and see how all these pieces kind of fit into kind of one unified framework. Okay, so let's talk about calculating joint angles. Oops. And remember, the framework that we're using is called unconstrained inverse kinematics. And so we're assuming, that's why we kind of have those 3 angular degrees of freedom, right? If we were to do constrained inverse kinematics, we'd be able to take kind of the geometry of the joint into account, because obviously like a hinge joint, like your elbow joint, doesn't have all 3 angular degrees of freedom. So you'd be able to do that. But for this, just because this one's actually relatively simpler, it's just our unconstrained setting. Okay, so let me start by saying so far, we've been talking, we've kind of been building up this idea of a framework for computing motion kinematics. So we have 3 things that we want to 3 things that we've kind of discussed here. Okay, so we have the idea of motion tracking trackers. Okay. Okay. We have the transformation matrices that we just finished kind of talking about. And then we have these idea of the different kind of reference frames that we're going to use. Okay, and so we have 2 reference frames that we usually use. We have the anatomical reference frame and the tracking reference frame. Okay. And so these 3 things together are going to allow us to compute the joint angles. Okay. Okay. So let's talk about how this is done. Okay. Okay. So whenever you start a motion capture study, the first thing that you have to establish is the kind of the different reference frames, the anatomical reference frame and the tracking reference frame. Okay. And so let me kind of remind you kind of the difference between the 2. Okay. So remember, for any given body segment, just for the sake of simplicity, we're going to assume that there's going to be no overlap. So, each reference frame is going to have its own unique 3 motion trackers. Okay. So for any given segment here, so this potato-looking thing, imagine this is an arm or something. Okay. Okay. So in orange, what I've drawn here is basically the 3 markers that can determine the anatomical reference frame. Okay. And if you notice, the way that I've drawn this, it's drawn to kind of align with the bones that are underneath the body segment. Okay. So that's going to be important because, for each body segment, so let's say your upper arm, your lower arm, your hand, right? We need these anatomical reference frames because, the difference between these is going to what's give us the our joint angles. Okay. Okay. So the idea is that to have a frame that matches up or is basically attached to the bones and aligns with the bones, because those bones are the most rigid thing inside your body segments, and so those are the best for joint angles. Okay. The challenge with this is that all the time all these trackers may not be perfectly visible to the cameras, right? And so as the person kind of goes through their motion, their body kind of moves around. The cameras may lose track of one or more of these trackers. Okay, and so to rectify that, we define a second set of trackers. Okay, so usually it's kind of something like this. Okay. Okay. So for the second set of trackers, their exact positions don't matter all too much, right? And so you can see here that I've kind of clustered them all into one area. So this is quite common as well. So this is what's called the tracking reference frame. Okay. And the idea with the tracking reference frame is to put these markers in locations that are easy to track, and so that they're pretty much almost always going to be visible to a camera, right? Because in order to kind of fully track a certain body segment, all three markers have to be visible to at least one camera. Okay. Okay. Okay, so these two coordinate systems are established. Okay. And then what we can do from here, so before any motion begins, and so before the person kind of moves at all, right? What needs to be done first is we need to kind of calibrate the system. Okay. And so what calibration basically means is that this person stands in a certain way so that all the markers are visible at once. Okay. Okay. Right. So this is important because what we have here is that using these two sets of markers, we have basically two different coordinate systems, right? So each of those trackers define an individual XYZ coordinate system. Okay. And so by calibrating, and by seeing all these markers at once, what we can do is we can define the transformation matrix between these two sets of markers. Okay. So that's the transformation matrix between, the tracking system and the anatomical system. Okay. Okay. So that's important. And so this is something we're going to use in our analysis. It's not the only transformation matrix we're going to get. In fact, we're going to be computing a lot of them, but this is one that's going to be used. Okay. And what's going to be even more important is that as the person goes through motion, right? So this person's body segment's going to be moving around, right? But because these two coordinate systems, the tracking system and the anatomical system, technically they're attached to the same segment, okay? And if we assume that that body segment is perfectly rigid, that means the relationship between the tracking system and the anatomical system for this segment is going to be static, right? So this transformation matrix that we just computed is static, or it's not going to change. Okay. And that's mostly just because these two systems these two reference frames are attached to the same segment. So they're going to move, they're always going to move together. Okay. And so this is nice because remember, even though we can't track the anatomical system at all points in time, okay, with this matrix here, if we can track the tracking system, which we should be able to do, that's kind of its job, you know, that we can use this transformation matrix to get the anatomical reference frame. Okay. So this is something that's going to be really useful for us. Okay. Okay, so we're going to keep this in mind. We're going to use it in a second, but you know, let's kind of remember that we have this system here. Okay. Okay. So that's during calibration. So during calibration, you know, the person kind of just stands still, and the computer kind of gets its bearings. Usually, the cameras are kind of fixed to kind of make sure they're focused on the right thing as well. Okay. Once motion starts, okay. Once motion starts, you know, we basically assume that we can't track the anatomical system anymore, right? So that's going to be basically unknown to us. Okay. But this tracking system, this tracking reference frame, we will be able to see it at all times. And in fact, we can kind of track its position. We can track its orientation by computing the transformation matrix of it relative to the stationary system, the lab system. Okay. Okay. So remember, you know, the way that we define the lab system, that's the reference frame, or that's the coordinate axes that are just fixed. And so it's you know, you put it in the corner of the room, or you can put it on any location, right? The idea is that it doesn't move with the body at all. So it's kind of our point of reference for measuring all motion. Okay. Okay. And so for instance, you know, this is going to be our lab and tracking. Okay. So this is one thing that we're going to be able to compute all the time. Okay. And in fact, this is something that is going to change with time, because the tracking system is going to move with the body. So the first transformation matrix that we had, that's stationary, that's static, that's not going to change. This one is going to change with time, because the lab frame is stationary, but the tracking frame is in motion. Okay. Okay. So that's good. And so, you know, we're going to be able to compute this for every single body segment, or at least every single body segment that we have motion trackers on. Okay. Okay. All right. So all this is just meant for a single body segment, right? But in order to get the joint angles, right, a joint is a joining of two adjacent body segments, right? And so we're going to need this information from an adjacent body segment. Okay, so ultimately, what we want is this transformation matrix between the anatomical frames of two adjacent body segments. Okay. And so this is what we want. So in our anatomical is such a big long word, anatomical 1 and anatomical 2. Okay. We don't have that, right? We can't track the anatomical frames as a function of time, but we do have, we have a few things. And so we have, we have the tracking frames relative to the lab frame, and we also have the calibration frame. Okay? And so what we're going to do is we're going to use basically, we're going to multiply a lot of transformation matrices in order to get this quantity here. Okay. Okay. So let me do a quick example. So we're not going to go through all the calculations just because, it's just basically all matrix multiplication, which you can do in MATLAB or in your calculator or whatnot. But I at least want to show you the logic in terms of how you can obtain this. Okay. So let's say that we're interested in tracking the knee flexion angle as a function of time. Okay. And so anatomically speaking, or at least kind of strictly, speaking, based on the anatomy, right? The knee flexion angle is defined as the angle between your femur, your thigh bone, and your tibia, which is the larger of your two lower leg bones. Okay. And so ultimately what we want is the transformation matrix between the femur and the tibia. Okay. Okay. But of course we don't have this, and so we're going to need to rely on the transformation matrices that we do have. Okay. So let's kind of take stock of what we do have and see if we can use them to compute this transformation that we want. Okay? So we want this. Don't have it yet. Okay. Okay, so the matrices that we do have are going to consist of the calibration matrices that we talked about before for both your thigh and your lower leg, and then as well as the tracking transformation matrices for the thigh and the lower leg. Okay. Okay, so we have the calibration matrices. Okay, so we have one for each segment, right? And so for the thigh, so I'm going to say that the one for the thigh is going to be the transformation matrix between the thigh and the femur. Okay. So I'm just using kind of the general term thigh just for the tracking system for the thigh, just because, you know, and the femur is kind of what we want. Okay. And then for the lower leg is a little bit long. So I'm going to call it the shank. Okay. So the shank is the same thing as the lower leg. Okay. And so we have the transformation matrix between the shank and the tibia. Okay. Okay. We also have the tracking matrices, right? And so even though we can't track the femur and the tibia in real time because of the locations of the trackers, we can track the thigh and the shank, you know, systems with time, right? So we're going to have the R thigh R lab as well as shank R. Okay. Okay. And so using these four matrices, we're going to use the transformation matrix kind of algebra, basically. Think of it as like algebra, in order to get the one that's above. Okay. So let's see how that we can do that. So let's kind of remind ourselves of some operations that we can use with transformation matrices. Okay. And so on the one hand, you know, if you multiply two transformation matrices together and their inner labels match, those inner labels are going to cancel out. Okay. Okay. And so, for instance, if we multiply R12 multiplied by 2R3, okay, the 2's here are going to cancel out, and we get 1R3. Okay. All right, so we're definitely going to make use of that. The other quality that we're going to use here is the transpose. Okay, and so when you transpose a transformation matrix, then its two labels are going to swap positions. Okay, and so if we take the transpose of, let's say, 1R2, okay, this is equal to 2R1. Okay, so just basically just swapping those positions. Okay. So let's use this information and let's compute the let's compute the order of operations using these four matrices to get this one up here. Okay. Okay. So what we want is femur, R, tibia. Okay. And so let's see how we can get there, right? And so we know at least we need to lead with femur, right? And so our femur needs to be kind of the leftmost index. And so the only transformation matrix among the four that we have is thigh R femur, right? So that's the one that has to go first. But femur here is on the inner index, right? We need to be the outer index. And so we need to take its transpose, okay? So we're going to have thigh R femur, okay? Transpose, okay? And so that transpose operation is going to put femur up top on the left and thigh on the bottom right. Okay. Okay. And so the way to kind of the logic that I kind of use for this is that, you know, you kind of go sequentially. You basically try to cancel the inner index, you know, as quickly as possible. Okay. Okay. And so now what we have on the right hand side here is thigh. So we need to multiply a transformation matrix with thigh to get rid of that. Okay. So beside the calibration matrix that we just used, the other transformation matrix that has thigh is thigh R lab, right? So let's multiply that. So we have thigh R lab. Okay. So that's going to cancel out the inner label for thigh. Okay. And then now our our rightmost index is lab, okay? So we're going to multiply by the other transformation matrix that has lab. So we have Schenk R lab, okay? But of course, lab is in the wrong position here, and so we need to transpose it in order to get it into the right position, okay? All right, and so the last matrix that we haven't used yet is Schenk R tibia, okay? And so let's go ahead and multiply that in. We need Schenk to be on the inside, so we don't need to transpose this. So it's going to be Schenk R tibia. Okay. Okay. So that's the exact order of operations that we okay. So the four matrices on the right hand side, we either know them because they're either constant, right? So the calibration matrices are going to be constant, whereas the tracking transformation matrices, those are going to change with time, or I should say they should change with the motion. And so then this one here is going to change with the motion as well. Okay. But using these operations, we'll be able to compute the transformation matrix between the femur and the tibia, and then we can use that to compute the joint angles. Okay. Okay. Any questions on this example here? Okay. All right. So a couple more points that I want to make before we go to the homework. Okay. Okay. So far, you know, these transformation matrices only account for orientation, right? And so they only account for angles. But you know, each of these reference frames, you know, they're going to be attached to different locations on the body as well. So there's kind of a translation component to this as well. Okay. Okay. And so we can state that as we can track the XYZ position of each of these reference frames relative to each other. Okay. All right, and so what this gives us, or the way to compute this, is we're going to basically just take the centroid or the origin of each of these reference frames and just subtract their coordinates from each other. Okay. All right. So for instance, you know, if we were to take, you know, the location of the centroid of the femur frame versus the location of the origin of the tibia frame. I keep saying centroid. It should be origin. Sorry, it's not centroids. Sorry, so that should be the origin of each reference frame, right? Because each reference frame has their own XYZ coordinates, and so those have to start at some origin. Okay. Okay. So for example, let's say that we have the origin of the femur. Okay. And so if we subtract that location from the origin of the tibia reference frame, This is going to give us a vector. Okay, so we'll call that P. So that vector P tells you kind of the relative position of the femur origin versus the tibia origin. Okay, and so almost always there's going to be an offset because each body segment is kind of located in different positions, and so this needs to be accounted for. Okay. All right. So the nice thing is that we can actually include this information into our transformation matrices, okay? And so we can basically augment it. Okay, so our usual transformation matrix is a 3x3 matrix, okay? So I'll go ahead and put that right there, okay? So just assume that that block right there is a 3x3 matrix, okay? This translation vector, this P vector that we just computed, can go to the right of that, okay? And so it's going to be a column vector. And then to make sure, we still have a square matrix, we're going to add the final row is going to be 0, 0, 0, 1. Okay. So this right here is the augmented transformation matrix. Okay, so the homework I think is going to have this, and so you should know how to do that. Okay. All right. So last thing we're going to talk about is how do we actually compute the angles from the transformation matrix. Okay. Okay. And so I think I kind of mentioned this a little bit briefly last time, but basically you're going to take the formulas for each entry of the transformation matrix as we've kind of derived so far in the class, and then use kind of the inverse trigonometry operations to get the angles. Okay, so for example, so let's take a 2D transformation matrix. Okay, and so a 2D transformation matrix has the following formulas, right? And so we have cosine theta, sine theta, minus sine theta, cosine theta, okay? Right. And so that's going to correspond to, another 2x2 matrix. So we'll call that R11, R12, R21, and R22, okay? And so what you would compute, in a mocap situation would be on the right? So you would just get a matrix of numbers, basically, okay? And so from that matrix of numbers, if you wanted to compute the angle, you would just simply take, maybe theta is equal to cosine inverse of R11, right? Or you can take sine inverse of R12, okay? And ideally, both of these should give you the same answer if you have a well-posed transformation matrix. Okay. All right, so that's basically what you're going to do in the homework. So basically, you're going to compute the numerical values of these matrices using the matrix kind of transformation matrix algebra that we discussed. So you're going to be multiplying matrices together, transposing them, and so on and so forth. Okay. And then to obtain the angles, you're just going to take like the inverse trig operations like this. Okay. Okay. And so in 3D, of course, we have a much more complicated case. So I'm not going to write out the whole equation again because that one's crazy. Okay. But our 3D transformation matrix is a 3x3 matrix. We have R11, R12, R12, R13, R21, R22, R23, R31 to R33. Okay. Okay. And so remember from our 3D transformation matrix, we have 3 angles we need to compute. Okay. And so there are quite a few ways that you can do this, but this is kind of the most recommended one, at least to give you the angles in the right ranges as before. Okay. Okay. And so actually the most recommended way is to use MATLAB. And so in MATLAB, there's a function called atan2. Okay. So it's a 2-argument or 4-quadrant inverse tan function. Okay. And so theta is going to be atan2 of R21, comma R11. Okay. Psi is going to be atan2 of minus R31, comma square root of R11 squared plus R21 squared. Okay. And then psi is equal to atan2 of R32 and R33. Okay. And so that atan2 function is in MATLAB. So generally I recommend using MATLAB for these ones. Okay, any questions on this before we kind of briefly just talk about the homework? Okay, all right, so for the upcoming homework, the one that was posted today, you're going to be doing these kinds of calculations. And so let's look at it just very briefly. Okay, let's not look at my picker anymore. Okay, 1, 23, homework 5. Okay, so this is what the homework looks like. And so problem 2 is going to be all about motion capture. And so part A is going to be for a 2D case. Okay, so that's kind of a starter case. And then part B is going to be for a 3D case. That one's going to be a little bit more complicated. Okay. Okay. So let's look at the 2D case first. Okay. And so for the 2D case, what we're going to say is that here is a 2D motion capture setup, and we want to basically set up all the transformation matrices to compute the angles. Okay. And since it's in a 2D system, instead of having 3 markers, you actually only need 2 markers to establish the system. Okay. You only need 3 in 3 dimensions. And so what this problem is telling you is that markers 2 and 3 here, those comprise the tracking coordinate system. And so we're going to assume that those ones are easier to track, whereas trackers 1 and 4 are used to establish the anatomical coordinate system. Okay. And the exact positions of these trackers are given to you in this part of the problem. Okay. Okay. And so part 1 of this problem is that I want you to use markers 2 and 3 to compute the 3x3 transformation matrix, right? And so between the lab coordinate system and the tracking coordinate system. Okay. So this is the tracking transformation matrix that we talked about earlier. Okay. And so you're going to use a little bit of a vector algebra here in order to do that. Okay. And so using these 2 markers here, right? So you have markers 2 and 3. What I tell you is that we're going to assume that marker 2 establishes the origin of the system. So marker 2 is where the origin is. Okay. And then the x-axis points from marker 2 to marker 3. Okay. And then the y-axis is kind of perpendicular to that location. Okay. Okay. And so to find the x-axis, basically, we have the locations here, marker 2 and marker 3, right? If you subtract these 2 positions, right? So you take, the difference between the x positions, 44.98 minus 39.14, and then the difference between its y coordinates, 59.55 minus 66.29. Okay, so that's going to give you a vector, and so that vector is going to point from marker 2 to marker 3. Okay, that's going to be the x-axis of your system. Okay, and then the y-axis is going to be perpendicular to that. Okay, and so I give you a hint here on how to find a vector that's perpendicular to that, and so you're going to perform a cross product. Okay, and so the cross product is going to be between the vector that we just found and a vector that goes out of the page. Okay, so even though it's a 2D problem, you're going to assume that there is a z-axis here that kind of points out of the page. So it's going to be 0, 0, 1, basically. Okay, so you're going to take the cross product between those two vectors, and then you're going to, obtain the y coordinate, and you're going to normalize it. Okay, and so normalizing means that you basically divide it by its magnitude in order to get, it to be magnitude 1. Okay, and so you're going to put all that information, and you're going to obtain the following, transformation matrix here. Okay, and so if you look at the first column of this transformation matrix, this is the x-axis. The second column of this transformation matrix, this is the y-axis. Okay, and then this last column right here, you can see is the position of the origin. Okay, so that's basically just the coordinates for marker 2, because that's where the origin is, right? So we have 39.14 and 66.29. Okay. Okay, and so part 2 of this problem, you're going to do the same thing except for the anatomical coordinate system. Okay, so you're going to do basically the exact same operations, and then you're going to perform, transformation matrix algebra from there. Okay, but I did want to go over this a little bit just because we didn't really do an example of kind of establishing the origin or doing vector subtraction to get the axes, but that's basically what you're doing. But it's not hard. It's just you just have to kind of cover it a little bit first. Okay. Okay, any questions on any of this before we move on? Okay, all right, and so that's homework 5. So that's posted for you guys, and so you should be able to do problem 2. It's going to be a lot of algebra, and so so just kind of be prepared for that. Okay. Okay. All right, so for the rest of class today, we're going to move on to the next topic in the class, which is inverse dynamics. Okay. All right, so in inverse dynamics, we're kind of following, like I mentioned before, we're kind of following the same kind of trajectory, the same path that you normally would in kind of a traditional kind of dynamics course, right? And so we just finished kinematics, okay? And so from kinematics, assuming we've set up everything correctly and we've computed everything soundly, we're going to be able to compute basically all of the angular kinematics of the person's body. Okay. Okay. So some examples of things that we have is maybe the positions of the centroids for each of the body segments. Okay. Okay. Joint angles. Joint angular velocities. Okay. And so to get the angular velocity from a joint angle, you just basically take its derivative with time. Okay. Oftentimes you're going to have to take this derivative numerically because you don't have kind of the expressions. Okay. And then if you have the velocities and you have the velocity data as a function of time, which you will, you can also compute the joint angular accelerations. Okay. So we have all of these quantities, okay? And so they are all we're from this point forward, we're going to assume that we have these quantities available to us. Okay. The next step in this process is to, now that we have these, now that we have these measurements of the kinematics, is to think about, what are the forces that were generated in order to kind of produce this motion. Okay. Because whenever you have motion, there had to have been some forces involved in some capacity, right? Motion doesn't just happen spontaneously. And so, that's kind of the next question that we want to ask, right? Because ultimately what we want to do, just like we did in the static portion, is to determine, if you have a certain kind of motion, if you have a certain kind of position, or a certain kind of, exercise, or a certain kind of activity, right? What are the joint reaction forces, and what are the muscle forces that are required to produce this motion? Okay. We're not quite there yet, and so we won't be able to compute individual muscle forces just yet. So that'll be kind of the main topic. We'll probably start it before Thanksgiving, but then we'll probably finish it after Thanksgiving. Okay. But at the very least, we should be able to get a good sense of the forces involved. Okay, and that's the idea of inverse dynamics. So the reason we call it inverse dynamics is that we're actually solving for the forces. So kind of forward dynamics or traditional dynamics, you kind of are given forces, and then you compute kind of the motion that results from the forces. Okay. Here we're doing the opposite. So here we have the motion, we have the kinematics, and we want to, based on our knowledge of the kinematics and the geometry of the person, we want to compute the forces that were involved. Okay. Okay, and so the reason I say that we can't compute the muscle forces just yet is because the muscle forces and the joint reaction forces are kind of more internal forces. Okay, and so what we're going to be able to obtain using inverse dynamics is more net forces and net moments. Okay. Okay. So for example, right? And so let's say that we have a body, right? We have a potato-shaped body. Okay. This body may be exposed to multiple different forces, right? So let's say that we have a force going to the right with a magnitude of 5,000 newtons. Okay. And let's say that we have an opposing force to the left of 1,500 newtons. Okay. Ultimately, what we want to do is and so based on the motion that we observe, we're going to want to be able to pick out these kind of individual forces. Okay. But we're not there yet. So all that we can do in this part is if we have the same geometry, okay, all we'll be able to compute is the net force, right? And so if you add these two forces together, okay, all we see is just kind of one net force that goes to the right. Okay. So the net forces are fine for overall motion, right? But usually when we're studying motion biomechanics, we're interested in individual muscles and individual joints. And the thing is, with the human body is that a lot of your muscles kind of produce kind of competing forces. And so you won't be able to discern what the exact force of a given muscle is, because maybe it does the exact same force as another muscle in the same direction, or maybe there's another force that's from another muscle that's opposing. Okay. We won't be able to get through this just yet, but we will a bit later. So we're going to focus more on this one here. Okay. So this is what's given to us in inverse dynamics. Okay. Whereas this one here, I don't know why I avoided that 5,000. This one here is going to be, we're going to need another tool. And so this one's called muscle force optimization. Those of you in my 454 class are rolling your eyes right now because you probably have enough optimization in that class, but we're going to see it a little bit in this class here too. It's not anything intense like before. It's a bit chill. That's going to be the next. That's going to be the next time. So we're going to focus on the one on the right. Okay. Okay. So that's kind of where we're going here. Okay. Any questions on this so far? Okay. All right. So before we get into that, let's take a brief detour and kind of remind ourselves of how we measure external forces. Because in order to compute, the net forces on each body segment, we also need to have some knowledge of any external forces acting on the body. Okay. Okay. So there are lots of tools that exist for measuring external forces. Just for our sake, we're going to be focusing mostly on the lower extremity, just because it's a little bit easier to compute. It's a bit more standardized. And so for the lower extremity, we talked about a tool before in gait biomechanics, which was the force plate. Okay. And so remember what a force plate is basically a plate that's on the ground. Okay. And so underneath the plate, we have you have basically load sensors. These are highly sensitive load sensors. In fact, they have a pretty short reaction time, and so any small changes, any kind of fast changes in force, they'll be able to sense it. Okay, so you can almost think of it as like a very fancy scale. Okay, but if you you've ever stepped on like a bathroom scale before, that's essentially what this is. But a bathroom scale is a little bit too slow to react. And so if you stand on any scale, you usually have to stand on it for a few seconds in order for it to get an accurate measurement of your weight. Okay. So these load sensors are calibrated much more tightly, and so they're able to sense changes much more quickly. Okay. Okay, so let's keep that in mind. And so I only bring this up just because in the examples that we're going to bring up, we're going to have some kind of external force acting on the foot, and the way that we usually obtain that external force is through a force plate like this. Okay. Okay. And so with that stated, let's go ahead and state what the inverse dynamics algorithm is. So remember, the objective of inverse dynamics is to compute, the forces and moments at on each of the body segments, okay? Or each of the joints, I should say. Okay. Okay. To accomplish this goal, we're going to need some data, and so we're going to assume that all the following will be given to us. They're either given to us or kind of easily obtainable. Okay. And so the first being a representative model of the subject. So we'll go over kind of exactly what that means in a second. Okay. But to perform inverse dynamics, kind of in a nutshell with that, it's really hard to perform inverse dynamics on kind of realistic geometries. Okay? So oftentimes you're going to have to simplify the geometry, but you want to do it in a way so that it still kind of respects kind of the essential anatomy and geometry of your of your subject. Okay. Okay. Number two is the subject's joint kinematics as a function of time. So that's what you would get from motion capture. So that was the last section that we went over. Okay. And number three is any measurements of external forces acting on the subject. Okay. So 2 and 3, we've kind of already talked about. So we kind of know at least what those are and kind of what to expect. Let's talk a little bit about 1, although there's not that much to talk about for there. Okay. A representative model. A representative model is basically just kind of a simplified geometry of the body segments in question. Okay. So this is not going to be a great example because both you can argue that both of these are representative models. They're both simplified geometries. But let's say that you have if we look at the arm, okay, and so the way I usually draw arms in this class is I use kind of just these blocky kind of segments like this, okay. But use your imagination. So imagine that that's a realistic looking arm, okay. Okay, but for inverse dynamics, we're going to just simplify this even further. So we often use these kind of thin, rigid rods connected by pin joints. Okay. Okay, so all of the dots here, these are all pin joints. Okay, so if you recall from kind of statics. A pin joint is just a simple joint that allows free rotation. Okay, Those pin joints can move, of course. So they, the positions of these pin joints depend on the positions of the body segments. But we're going to assume basically frictionless rotation. Okay. And then the lengths of each of the rods correspond to the lengths of the body segments. Okay? And so what we have here on the right here is our representative model. Okay. Theoretically, you could build this in a lab, right? So if you have thin rods and you have pin joints, you can kind of construct the same. Okay. So the only reason we do this is that it makes the calculations a lot easier to do. Okay. Okay. So now that we have our representative model and we have our kinematics and we have our external forces, okay, the way that we're going to proceed, or the way that inverse dynamics works, is that we're basically going to do the same thing that we did in static analysis, right? So we're going to write out all of the equations of motion and kind of solve each of those sequentially. Okay. And the important thing is that we're going to write out these equations of motion for each body segment, okay? And so if we have kind of 3 body segments involved, that means 3 sets of equations of motion, okay? And so things can actually scale up quite a bit because the more body segments that you involve, the more equations that you have to solve for at the same time, okay? Okay. And so for each segment, basically, we're going to have a sum of the forces. Okay. We're going to have 2 sum of the forces. So typically, we sum the forces in the x and y directions, just because those are pretty standard. So that would be the lab x and the lab y, right? And the only difference here between here and statics is that instead of equaling 0, we're going to have this equal to be the mass times the acceleration. And then we're also going to have the sum of the moments. Okay. Okay. The moment equation is going to be interesting because on the one hand, you have the angular component. Okay. And so you have the angular component. The sum of the moments is going to be equal to the moment of inertia multiplied by the angular acceleration. Okay. But you also have the component that has to do with the rotation of the center of mass itself. Okay. So this is going to be plus RP cross product with mass times acceleration. Okay. We'll talk more about that kind of that last term in a second. But just know that you're going to have these 3 equations for each body segment. Okay. And so if you have 3 body segments, that means you're going to have 9 equations overall. Okay. And generally, the unknowns in these equations, for the most part, are going to be the net forces, x and y forces at the joints, as well as the net moment at the joints as well. And generally for these problems, we're going to set them up in a way such that the number of joints in the geometry is going to be equal to the number of body segments, right? And so that way you'll have enough equations to solve for the unknowns. Okay. And so, for example, for this situation here with the arm, we have 3 body segments. We have the hand, we have the lower arm, and the upper arm, and we have the 3 joints here as well. So we have the wrist joint, we have the elbow joint, and the shoulder joint. Okay. And so using this process here, you'll be able to compute, you know, the joint reaction forces and the net moments at each of those joints. Okay, so 9 unknowns and the 9 equations that are solved. Okay. Any questions on this so far? Okay. All right. So the last thing I want to mention today is to expand a little bit more on this moment equation. Okay. Specifically, this last term right here. And so this RP vector multiplied or cross product with MA. Okay. Okay. So let's talk a little bit about what that represents. Okay. All right. So let's first define each of these terms. So let's define RP vector. Okay. So RP is a vector, as the arrow on top implies, and where this points is that it points from. I should say that points from the location where the moments are summed around. Because whenever you're summing moments, you have to have some kind of reference point. That's where you're kind of referencing everything from. Okay. From that location to the centroid of the body segment. And again, this is kind of accounting for the fact that that center of mass, or that the mass of that segment, is also going to be rotating with some speed as well. Okay, and the main reason why we have to have this term is that this moment of inertia that we compute, okay, that I term that's part of that equation, that moment of inertia is usually computed relative to the centroid of that body segment. And so you can almost think of this RP term as kind of almost like a correction, right? And so this is kind of a correction due to the fact that the location that we're summing the moments around is not the same as the moment that, or not the same as the location where our moment of inertia is taken from. Okay, and so because there's that discrepancy between the moment of inertia and the part that we're summing around. That's why we have that term. We're not always going to have that term, and so there are going to be times where we sum our moments around the centroid of the body segment, and so in that case, that RP term is going to go away. But a lot of times we are going to sum the moments around a joint. That's kind of the most natural thing. And so if we're going to sum our moments around a joint, then we have to have this correction term that involves RP. Okay. All right. Any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got for today. And so when we come back on Monday, we're going to do a couple of examples with inverse dynamics. So you're going to see kind of the whole process kind of laid out, and then we'll go from there. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your weekend. Make sure you guys are thinking about the projects, and so you definitely want to form your project group soon, and pick a topic before they're taken up. And so if you have your group, if you have your topic, send me an email just so I can kind of reserve it for you. And so you can start working on the project. Okay. All right. So thank you guys for coming. Hope you have a good weekend, and I will see you guys next week. Question, so is inverse dynamics going to be on the second midterm? It will be on the second midterm. Yeah, so second midterm is basically going to be homework 4 and homework 5. So if you look at the last problem of homework 5, that's inverse dynamics.
Professor, I just had a question on
Thanks,
the
guys.
sum of the moments equation up top.
Oh, sorry, hang on. I need to increase the volume. I hear your voice, but I can't hear what you're saying. All right, say
It's
again?
all good. Hi, Professor. I just had a question about the sum of the moments equation. If you scroll up a little bit.
Yeah.
Where it's the sum of the moments is the moment of inertia. It was is that alpha or what is that
Yeah,
second?
it's alpha. So alpha is the angular acceleration.
Oh, angular acceleration. Okay.
Yeah.
Okay, that was it. Thank you, Dr. Tran.
Yep, no problem. All right, Zoom, any final questions before I wrap it up? All right, see you guys next week.